Okay, so in this video, we will consider an example of hypothesis testing in the case of independent samples, and we are going to test for a difference of two proportions. So here's the problem. A company manufactures USB memory keys in two different factories. A random sample of 200 USB keys from factory 1 were inspected and 12 were found to be defective. A random sample of 300 USB keys from factory 2 were inspected and 34 were found to be defective. So part A, we want to test at the 4% level of significance the claim that factory number 2 has a greater proportion of defective USB keys than factory number 1. In B, we will construct a 98% confidence interval for the true difference of the proportions from factory 1 and factory 2. And in C, we are going to ask whether or not the conclusion of part A and B, if they are consistent with each other. So let's start with part A. So we have our two samples, the sample from factory 1, 200 USB keys. So we'll call this N1. And R1 is the number of subjects, of items from the first sample that have the desired characteristic. Here we are looking for the proportion of defective USB keys. So for us, we're looking at defective USB keys. And out of those 200, 12 were found to be defective. So R1 is simply 12. So we now have our sample proportion from sample 1, which is P1 hat, which is quite simply 12 over 200. And we have its complement Q1 hat, which will be 200 minus 12, which is 188 over 200. And now we can do the same thing for our second sample coming from factory 2. And you see here we can assume independence because factory 1 is producing the USB keys independently of factory 2. So from factory 2, we obtain a sample of 300 USB keys. And out of those, 34 were found to be defective. So again, from sample 2, the sample proportion of defective USB keys is simply 34 out of 300. And the complement for P2 being Q2 hat is of course 300 minus 34, 266 over 300. So now we look at our statistic, and if you remember, since we have a test of hypothesis, we will use the corresponding statistic. Let us write our two hypotheses. Oh, and remember that here we are testing at a 4% level of significance. So we can write alpha is 4%, 0.04. Let us find our p bar and q bar because we will be pooling our samples. Because what we have here is a test of hypothesis. So p bar, if you remember, is the proportion of defective USB keys in our case after we combine our two samples into one larger sample. So if we combine our two samples, we have 500 keys in total. And out of those, a total of 46 were found to be defective. Then we have the complement, Q bar, which is simply 1 minus P bar. Again, this is out of 500. And if you do 500 minus 46, you get 454. So now we have the proportion for our pooled sample and its complement. So now we're good to go. So what will be H0 and H1? Well, we are considering proportions of defective USB keys from two factories. As always, H0 is the hypothesis of no change. Therefore, that there is no difference between the proportion of defective USB keys produced in factory 1 and in factory 2. So if P1 is the true proportion of defective USB keys manufactured by factory 1, and peak 2 is the true proportion of defective USB keys manufactured in factory 2, their difference under H naught will be assumed to be 0. Right? So the hypothesis of no change, therefore there is no change between the two proportions, they're therefore equal. So the difference is 0. And in H1, what is the claim that we're trying to test? Right? We want to test the claim that factory number 2 has a greater proportion of defective USB keys than factory number 1. Well, think about it. We are considering P1 minus P2. If the claim is that factory 2 has a larger proportion of defective USB keys than factory 1, then P2 would be bigger than P1. But if P2 is bigger than P1, P1 minus P2 will be negative, therefore less than 0. So now we have our two hypotheses. Let us construct our rejection region. Well, if you remember, our statistic, and I'll write it here when we compute our observed value, follows the Z distribution. Sorry about that. And so if we draw our standard normal distribution, the mean is therefore 0. And which part are we rejecting? Well, we have a left tail test, right? This is less than 0, therefore to the left. So we are going to reject the smaller 4% of values. So this is the classic inverse z-score. We know the probability to the left of our score. We want to find the z-score. So look in your table of the standard normal distribution for the probability closest to 0.04 you can find. And if you do so, you will find a corresponding z-score of negative 1.75. And so we now have our rejection region. It is from negative infinity to negative 1.75. All we need now is our observed value of our statistic. So let's see. So what is our statistic? If you remember, in the case of a test of hypothesis, it is P1 hat minus P2 hat minus P1 minus P2 over the square root of P bar Q bar 1 over N1 plus 1 over N2. And this follows approximately the standard normal distribution. And if you look, both samples are well above 30, so everything is okay. Now all we need is to compute our observed value of Z. So we'll call this Z, as always, subscript OBS for observed. And then we just replace. P1 hat, we found to be 12 over 200 minus P2 hat, which we found to be 34 over 300 minus, and if you think of it, well, what do we take for P1 minus P2? Well, we are under the assumption of H naught, and under H naught, P1 minus P2 is equal to 0. So all we do is we subtract by 0, therefore this term simply vanishes, and we divide by the square root of, well, our P bar times Q bar, so they're here, 46 over 500, 454 over 500, times, if you remember, 1 over, well, it's right here, 1 over n1. n1 was 200, so 1 over 200 plus 1 over n2, and n2 was 300. So with your calculator, you can now compute this, and you will find an approximate value of negative 2.02. And if you look, negative 2.02 is less than negative 1.75, and so our observed z-score does belong to our rejection region. Therefore, our conclusion is that we reject H0. Well, if we reject H0, we will accept H1, therefore, that the difference between P1 and P2 is negative. So if you simply add P2 to the right, this is equivalent to saying that P1 is less than P2, or, of course, P2 is greater than P1. And so we have confirmed up to 4% that the conclusion here is correct. That factory number 2 has a greater proportion of defective USB keys than factory number 1. Because we have accepted H1, therefore that P1 minus P2 is negative, therefore that P2 is indeed greater than P1. And that's it. And so you see, other than finding your pool proportion and the complement, and a slightly stranger statistic, everything else works the same. Let us now consider part B. Well, what is part B? We want to construct a 98% confidence interval for the true difference between the proportion of population 1, so factory 1, and the proportion of factory 2. And now we will, of course, use the other statistic for the difference of two proportions. So again, we have 98% confidence. So 0.98 is our confidence level. Let us write our statistic. For a confidence interval, it is going to be P1 hat minus P2 hat minus our parameter P1 minus P2 over the root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. And because both samples are way above 30, this will be following approximately the standard normal distribution. So this is our statistic. As always, first let's construct a 98% confidence interval for Z. So we can draw our distribution, being the Z distribution, the standard normal. We want the central part of our distribution to have an area of 0.98. This is a rather bad picture because it will be symmetric about 0. That's 0.98 in the middle. That leaves 2% for the two tail ends. By symmetry, they both must have an area of 1%. Now if you look in your table of the normal distribution, the standard normal distribution, and you look for the closest that you can find to 0.01 for a probability, you will find a corresponding z-score of negative 2.33. By symmetry, the point here must be 2.33, and that is your critical z-score for a confidence level of 0.98. Well, as always, we now have a 98% confidence interval for z, right? The probability that z lies between these two values is 98%. And now, well, we wanted a confidence interval for P1 minus P2. So as always, we will replace z by our statistic and isolate our parameter. Let me just write it here. So we have, and I'll just write negative ZC here. So negative ZC is at most our statistic, so P1 hat minus P2 hat minus P1 minus P2 over the root of P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2, and this will be at most ZC. Now we'll leave the algebra up to you because this is something we've done several times before. You want to isolate this, so you'll multiply across by the square root, and you'll have then a difference between the sample difference and the true difference. So you'll have the error in ZC times this. So let's just write this. This would be the error. And then you will subtract both sides by this. And finally, if you multiply across by -1, you will have isolated the true difference between P1 and P2. And so you will have as a confidence interval the following result. The left-hand point will be the sample difference minus the error. And the right-hand point will be the sample difference, as always, plus the error. And if you go back, we have everything here, right? Our value of ZC is 2.33. We found P1 hat, which was 12 over 200. P2 hat was 34 over 300. So then you can compute, and of course N1 was 200, N2 was 300. So you can find your error, subtract that to the sample difference, add to the sample difference, and then you will get your 98% confidence interval for P1 minus P2. And here's what you should find. It will be at most 0.00454 and at least negative 0.111. And this is our 98% confidence interval for the difference between the true proportion of defective USB keys manufactured in factory 1 and the true proportion of defective USB keys manufactured in factory number 2. If you remember in part C, the question was, are the results of part A and part B consistent with each other? Well, this is our conclusion from part B. This is our 98% confidence interval. So we are 98% confident that the true difference between P1 and P2 lies between negative roughly 0.11 and basically 0. What was our conclusion from part A? If you remember, we rejected H0 and accepted H1, and the claim in H1 was that P1 minus P2 is actually less than 0. Or, if you prefer, P1 is less than P2. Same thing. Well, let's see if they are consistent. Let's visualize this on the real line. Here's 0. This is our right-hand point, 0.00454, so it's really, really close to 0. I'll exaggerate here just for clarity. So this is 0.00454. And the left-hand point is roughly negative 0.11. And so we are 98% confident that the true difference between P1 and P2 will lie in here. Oops. Sorry, this is positive, so I've actually reversed them. So this is the value here, slightly bigger than 0, and this is 0. So our interval goes all the way up to this value, 0.00454, slightly bigger than 0. So this is our 98% confidence interval. And so you see, if we're being technical about this, if we're being very picky, it seems that both are inconsistent, because you see that part of our interval contains positive values, right? So here most values are negative, and you say, well, okay, if P1 minus P2 is negative, add P2 on both sides and you get that P1 is less than P2. But if we look at just this tiny portion of our confidence interval, then this interval contains positive values from 0 to 0.00454. It's a really small interval, but does contain positive values. And so then P1 minus P2 would be positive. If we add P2 on both sides, P1 is then larger than P2, which seems to go against our conclusion from part A. But if you think of it, if you use your intuition here, you're saying, well, if you play the odds, is P1 minus P2 more likely to be in the negative part of your interval or in the positive part? Well, the negative part is much greater, much larger than the positive part. So the odds are that P1 minus P2 will actually lie in the negative part, because the positive part is just so small compared to the negative portion of your interval that it seems way more plausible that P1 minus P2 is in this part, the negative part, and therefore that P1 minus P2 is negative, therefore that P1 is indeed less than P2. So again, if we're being very technical about this, it seems that we have a bit of a contradiction, because it is possible that the difference is in this tiny part of our interval, which means that P1 minus P2 is actually positive, therefore that P1 is larger than P2. But if we're being realistic, the odds are that most likely P1 minus P2 will lie in the much larger negative part of our interval, and so indeed P1 minus P2 is negative, therefore the P1 is less than P2, which does support our conclusion from part A, that factory number 2 manufactures more defective USB keys than factory number 1 in terms of its proportion.